We'll start our chapter 21. So first half we discussed about the conduction with thermal energy generation. So now I'll show you the derivation of the equations. So today I'll show you mainly the derivations of the plane wall heat generation, and then subsequently we'll do some numerical solutions. And then in the next class, in the Friday, we'll discuss about heat generation in cylindrical wall and cylinders and spheres. So let us see how this what happens. As you can see, heat conduction with internal heat generations, actually it's been encountered in terms of like nuclear reactors. Some fuel rods are there, or in case of electrical conductor during chemical and combustion process and drying and settling of concrete. Okay, so as you can see, the figure you can see here, it's a plane wall of thickness L. It's given the thickness L. Of uniform thermal conductivity K, in which heat sources are uniformly distributed in the whole volume. Let us assume the wall temperature are T1 and T2. We can give it TW1 and TW2. And we also consider an element of thickness distance at a distance x from the left hand side of the free wall, which is having this element. Actually, there is a heat generation happening. Okay. So heat conduction in the distance x is given by a Fourier's law Qx minus Ka dt dx. Now heat is being generated in this small element of thickness del dx can be given by Qg is equal to A dx into Qg. Here that small capital Qg is the total amount of heat being generated, and small qg is given by the heat generated per unit volume per unit time in the element. Okay, that is the amount of heat being generated. So this is the volume, and then the per unit A dx is the volume, and then Qg is the heat generated per unit volume per unit time. Now heat conducted out at the distance x plus dx. So since the heat is being generated, so there will be some heat conduction at the. So heat input is Qx and the heat output is Qx plus dx. So heat conducted out at distance x plus dx can be given by Qx plus dx, Qx plus d by dx, Qx dx, because that is the amount of heat, first derivative of the amount of heat which is being generated at this wall. That is being dissipated, right? So they have to take first derivative. Now Qg is represent the energy increase in the volumetric element, right? So if you do an energy balance, what will happen? Qx plus Qg, that is the heat conduction at this wall, plus the amount of heat generated is equal to Qg, will be the total amount of heat being dissipated at the other side, that is Qx plus dx. Okay, so Qx plus Qg will be Qx plus dx. Now Qx plus dx is also been given by Qx plus d by dx, Qx dx. So you write down Qx plus d by dx, Qx dx. So Qx get cancelled, you get Qg equal to d by dx, Qx dx. Now Qg also you have written A dx Qg. So substitute A dx Qg, and d dx, Qx is also being known minus K dt dx. You write minus K dt dx dx. So what happens? This is the second derivative of, because K and A is constant, comes out minus K. So it's over d2t dx to dx, right? So this is the equations. Now dx dx cancel, A get cancelled, and then Qg by A, Qg by this become Qg by K on the left hand side, which can comes to the right hand side, or this term can go to left hand side. It's become d2t by dx2 plus Qg by x0. This is the expression we talked about in the morning. If you remember correctly, this 2.88. This is the expression we talked about this morning. I did not show you how to come to this equation, right? So this equation again can be, this is a differential form of this heat generation. Then it can be solved with the proper boundary condition. That is what I discussed in the first class. So if we take first derivative, then it will become dt by dx equal to qgx plus c1, and then again if you take another derivative, it becomes t equal to qg by 2k x2 plus c1x plus c2. Hope you understood up to this point. So this is the expression, this 2.89 and 2.920 you get by doing the integration of this equation, right? So now how to solve it? Now you refer to this figure 2.92, and we consider that x equal to 0, t is t1, right? Or tw, it can be given, and x equal to kl, this at this halfway through, t can be given by t2 or tw, right? So at tw is the temperature of the wall surface. So using these boundary conditions, in the equation 90. 90 means this one, right? 90 is this expression, right? So put this equal to 0, t equal to t1, y equal to tw, and x equal to l. X equal to l here again, t equal to t2 equal to tw. So you are considering that the temperature is uniform, right? Temperature is uniform. So you put the value of, substitute the value of C1 and C2 in this parent equation 2.90 is become T become Qg by 2k s square plus Qg by 2k ls plus Tw. Or you can write T equal to Qg by 2k l minus x times x plus Tw. In order to determine the location of the maximum temperature, so this is the expression. If you need to the maximum temperature, I think I told you we have to do the differentiation of the first this expression, equation 9.1, 2.91, and then set it at 0. So dt by dx, Qg by 2k l minus 2x, and it will be equal to 0. So Qg by 2k cannot be 0, so l minus 2x becomes 0. So x equal to l by 2. So the maximum temperature happens at the halfway through, right? So the distribution of the temperature given by equation 2.91 is a parabolic and symmetrical about the midplane. The maximum temperature occur at x l by 2, and its value is Tmax. So l by x equal to l by 2. You can put l by 2 here. So Tmax will be Qg by 2k, L minus x by x into L by 2 plus Tw. You put all the value, it becomes Tmax Qg by 8k L square by plus Tw, right? So this is the maximum temperature, Qg by 8k L square plus Tw. Heat transfer then takes towards both the surface, and for each surface is given by Q equal to minus k dt by dx equal to x equal to 0 and x equal to k, right? Because x equal to 0 here and x equal to L here. So minus k dt by dx is already determined, right? Qg by 2k l minus 2x dt by dx, Qg by 2k l minus 2x. You put this value, and then x equal to 0 and x equal to k. When x equal to 0, this is become al by 2 into qx, right? Because this expression, right, if x equal to 0, this term get cancelled, so it become minus ka. Kk get cancelled also, so it become Qg al by 2. If both the surfaces are considered, then it become Q equal to 2 by, so if you put L, then it will become Q equal to 2 into Al by 2 Qg, that is Al by Qg. Also, heat conduction to each wall surface is further dissipated to the surrounding atmosphere at temperature T0, Tw. This is the surrounding temperature Tw. Thus, delta Al by 2 Qg, this expression equal to, if it is by this is the heat conduction, heat loss by convection. This is HA Tw minus T0, right? Surrounding temperature is considering T ambient. So actually it become, then Tw is become Ta plus Qg by 2H into L. Now substituting value of Tw from equation 2.91. Tw is this expression, right? We obtain T equal to Ta plus Qg by 2H times L, Qg by 2k L minus x by x equal to L by 2, that is at the midplane, T equal to Tmax, which is given by Ta. So just substitute this value. But Tmax is given Ta plus Qg times L by 2H plus L square by 2k. Now this expression 2.95 also works in OL in case of conduction and insulated wall. For an insulated wall, boundary condition apply at x equal to L, dt by dx 0, and at x equal to 2L, t equal to Tw, right? The location of x equal to L refer to the midplane and the hypothetical wall for instance. So you just put the value of this and then you solve it to get T actually Tmax Qg by 2k into L square plus Tw. This is the expression for the insulation wall. So this expression, you remember this expression, this expression, this expression. That will be critical for numerical solving, okay? Now another case we need to consider, this is a little complicated one. Both the surface of the wall have different temperatures. So initially we considered the temperatures are uniform, right? Tw. But if you consider that the temperatures are not uniform, then what happens? Here it is Tw1, it is Tw2, right? Temperature gradient exists. So if you see reflect 2.93 at x equal to 0, T equal to Tw1 and x equal to L, T equal to Tw2, right? Then substitute this value C1 and C2, you get this. Similarly, then T become like this expression. It's a complicated expression. Now the temperature distribution is dimensionless form can be obtained by making the following transformation. T minus TW equal to, just taking the side, T minus TW, because TW we have calculated, Qg by 2k L square x by, this expression is this, and then you divided by T minus TW by TW1 minus TW2, right? So then this is the expression. Now if you replace this parameter Qg by 2k L square by TWNS minus 2 by a constant factor Z, then we get this expression, right? This is the expression, and then in order to get the maximum temperature in location, this expression needs to be differentiated with respect to x and then set it 0. So if you do this expression, divide by x by L and then set it at 0, then it becomes x by L becomes Z minus 1 by 2Z. Thus, the maximum value of temperature occurs when x by L equal to Z minus 1 by 2Z, and the value is given by Tmax. Now you put it here. Tmax minus TW2, TW minus TW2, and then x by L you put Z minus 1 by 2Z, and solving it you get Z plus 1 whole square by 4. This is the expression. So as the value of Z increases, the slope of the curve changes. You can see Z plus 1, plus 2, 0, minus 1, right? Then this increases, slope of the curve changes. Obviously, the direction of the flow can be reversed by the adequately large value of Qg. When Z equal to 0, this is the temperature distribution linear. You can see it is linear, right? That is no internal heat generation. When the value of Z is negative, here Qg represents absorption of heat within the wall. So there is no heat dissipation, it is heat absorption. So these expressions are low, it will be, I mean, cumbersome, but again, it is, I mean, if you can get this thing done first off, then it will be easy for you. But again, if I give you any numerical, I'll definitely provide you the equation, nothing to bother. So let us look into a couple of numericals before we move to the next chapter. So it is given the rate of heat generation in a slab of thickness 160 millimeter. Thermal conductivity given 180 watt per meter C is 1.2 times 10⁶ watt per meter cube. If the temperature of the each surface of the solid is at 120 C, it is 120 both the surface. Determine the temperature of the mid and quarter planes, mid plane and quarter plane. Okay, the heat flow rates are temperature gradient at the mid and quarter plane. So all the parameters given, right? You have referred to this figure. So this is L by 2, this is L by x equal to 3L by 4, this is x equal to L by 2, this is x equal to L by 4, this is x equal to 0. Total is L. The thickness of the slab L is equal to 160 millimeter given, 0.16 meter. Rate of heat transfer Qg is given, 1.2 10⁶ watt per meter cube. Thermal conductivity given, temperature of each surface given. The temperature distribution is given by this formula. I think you have already seen equation 2.91. Equal to Qg by 2k L minus x times x plus Tw, right? So at midplane x equal to A will be L by 2. Midplane temperature will be, then you just put the value of this equal x will be L by 2, and then you solve for it, you get 141.33. At quarter plane x will be L by 4 and x will be 3L by 4. So at x equal to L by 4, you get 12, you get 136. Similarly, x equal to 3L by 4, you will get 136. Very simple. Just you need to use this equation and then substitute a different value of x, L by 2 and L by 2, 3L by 2, CL by 4 and L by 2. Now heat flow rate and temperature gradient at the mid and quarter plane. We are considering 1 meter square unit area. Heat flow rate given by Qg Ax, that is the total amount of heat, right? Qg already know AU1 and x is equal to L by 2, right? Because for the mid plane it will be L by 2. So this will be 96,000 watt per meter square. Similarly, heat for L by 4 it will be 48,000 watt per meter square. The temperature gradient formula is Q minus Ka dt by dx, or dt by dx, that is the temperature gradient, you will be minus Q by Ka. You already know Q, so A also 1, K you know. So if you just derive, then it will be minus 533.6 degrees C per meter, and for the 3L L by 4 it will be minus 266.67 degrees. That's all. I hope you understand this problem. Only thing you need to remember is this expression. To know this expression, then you can solve this problem. Let us look into another problem. A plate 2 centimeter thick and 10 centimeter wide is used to heat a fluid at 30 C. The heat generation rate inside the plate is 7 into 10⁶ watt per meter cube. Determine the heat transfer coefficient to maintain the temperature of the plate below 180 C. You have to determine the heat transfer coefficient, that is K. Given K of the plate 26 watt per meter C. Neglect heat losses from the edge of the plate. Thickness of the plate given 2 centimeter, that is 0.2 meter. Temperature of the fluid to be heated given 30 C. Heat rate given 7 into 10 to the 6 watt per meter cube. Maximum temperature of the plate is given 180 C. Thermal conductivity of the plate given 26 watt per meter C. So heat transfer coefficient H is the following expression. You already derived this, right? If you remember, this is the expression. I think if you remember, this is the expression, right? This is the expression Tmax Ta plus Qg L by 2H plus L square by 2K. Right, this is the expression we are using. Tmax equal to Ta plus Qg into L by H plus L square by 2K. Maximum temperature given 180, fluid temperature given 30 C, Qg given, L given, H you have to determine, right? So you substitute the value and then solve for H, you get 512.8 watt per meter. So that's all. So it's very easy, just one expression. So I think this has been repeated. Another problem. Sheet of glass coated on one side with an exceedingly thin but transparent electrically conducting layer is mounted vertically in a room where air is at 20 C. An electric current is passed through the conducting layer to generate heat at the rate of 2.5 kilowatt per meter square of conducting material. If the mean heat transfer coefficient on both sides of the sheet is given 10 kilowatt per meter per C, find the temperature on both sides of the glass. The glass thickness is given 6 millimeter. Neglect the thickness of the conducting layer. It's a very nice problem. A sheet of glass is insulated material, right? So you all know. But it's coated on one side with an exceedingly thin but transparent electrically conducting layer. So this is the exceedingly thin but electrically conducting layer is being given, right? Glass thermal conductivity given 0.7 watt per meter Kelvin. Ambient temperature is given 20 C, right? Air temperature is given. Q is given to the heat transfer rate, right? 2.5 kilowatt per meter square, that is 25,000 watt per meter square. And then H, that is the thermal heat convective heat transfer coefficient, right? Heat transfer coefficient both sides of the sheet given 10 watt per meter square C. K for the glass and then L 6 foot. You can see glass thermal conductivity given, the thickness of the sheet is given 6 meter. Then convective heat transfer coefficient given H. We are considering the temperature at the both sides T1 and T2. Ambient temperature is given how much? 20 C. Right. So it's a problem of the similar problem what we did. Consider the surface area. We can consider surface area 1 meter square. So H T1 minus Ta, that is the convective heat transfer coefficient on this side, plus H T2 minus Ta. That will be the total convective heat transfer coefficient, right? That is 2500 watt per meter square, right? This is what actually been given, right? Or you can write H T1 plus T2 minus 2Ta 2500. I hope you understand this. This is the amount of heat loss, right? At this wall and this side, which is equal to the total amount of heat loss, right? It is given actually a total amount of heat generation, right? Which is given 2.5 kilowatt per meter square. So this is the expression then, or you can write H T1 minus Ta plus K T1 minus T2 by L, because we know this is for the convective, but then if you have a convective as well as conduction heat transfer, then that will be also equal to 2500, because this is the convective heat generation, this is the conductive heat generation between the two ones. Now the substitute this value we get, you solve for it, you get different parameters, then you solve, you get T1 equal to this expression. Now substitute the value of T1 in equation 1, that is this expression. We get T1 is how much? We got T1. T1 is this much, right? So you have substitute the value of T1. And then you solve for T2, you get T2 160.78, and then you can use this expression to get T1 169. So this side is 169, this side is 160.78. This is very nice problem, but basic fundamental concept you have to use. No need to use any kind of expression or equation, just the heat generation, right? by convection and convection and conduction. That's all. This is convection, this is convection and conduction. And then solve these two equations.